Oh, can people hear me? That was so crazy. It's like I was saying one thing and the next thing I was like, oh my God, what happened? Which means I'm going to have 2 recordings, as you can see here. Now I'm going to have, just sucks. I'm going to have 2 recordings I have to upload, basically. Damn it. Okay, I'm so sorry, guys. Sometimes you have those days with your computer. Yeah. I'm sorry about that. This sucks because you see, as this is rendering, I'm going to have 2 recordings. Okay, it's fine, whatever. So yeah, I was saying that, like, you don't know if the actual difference, the reason why the p-value depends on the alternative is because you don't know if the difference is back here or if it's up here. So which means that you have to multiply your p-value you get by 2, because when you look up the p-value in the table, remember, it only gives you the area above, but we know that the area behind, right, is proportionally the same. So we know that, like, the area back here, right, the probability of, like, z less than negative z is equal to the probability of z bigger than z. We know this is true. So this means that when we're looking at the area back here, it's the same as the area to the right here. I guess we should be a bit more like this, right? So we know this is the same thing as the area above. So which means that when we look at this hypothesis, we have to multiply it by 2, because all we were looking for in the table would be the area, like, up here, but we need to consider the area behind, right? So we multiply it by 2. But if it's only a one-sided test, actually, you only have to multiply it, but you don't multiply it by 2 because you're only looking at one side, right? So if it's a one-sided test, so this is why Ramil's question was a good one, because if your test is one-sided, you need to be very careful. You shouldn't multiply your p-value by 2, right? So definitely scan the question to see if I said things like different, less than, equal to, because that would indicate as to whether or not you should be multiplying your p-value by 2. And implicitly, because you multiply your p-value by 2 in a two-sided test, this makes the test more conservative, because when you multiply a p-value by 2, you make it twice as hard to reject the null, right? So it becomes a more conservative test because of that. So let's go back to our little example here. This is referred to as a contingency table. So for those of you who are looking at your project, doing your projects, please know this is the kind of table you want to actually look at, construct. And notice that, and this is good, by the way, going to be the table we use for inferential statistics, right? So each row is a category of the explanatory variable, right? So prayer, because we know this is the explanatory variable here, did they get a prayer, yes or no? This is the group of people who got a prayer. These are those who did not. The response variable always happens in the column space. So this is a column. The outcome, yes, they had complications versus no, they did not, is in the column space. So please be mindful. Whenever you construct your question for the assignment, think about whether or not, if you have any questions, please email me or put it in the discussion board so you can ask, is it true that in my mind, I've determined whether or not, what is the response variable, what is the predictive variable, right? So for instance, the context of, like, let's say distance education, you may think that, do those who, feel that distance education had impacted their grades negatively, yes versus no, are they more likely to believe that, or are they less likely to believe that, this is online learning should be a thing that continues after the pandemic, right? So the way I frame the question, I'm saying that, like, are those who experience negative consequences of the distance education less likely to be proponents of, like, online learning post-pandemic? So I'm implicitly saying that the explanatory variable is whether or not people felt online learning impacted their grades, right? So this is, you have to think to your mind, what do you think first preceded the outcomes? What is the outcome you're interested in looking at? If it's whether or not someone says yes or no to online learning, then that's your outcome, which means the thing that comes before it is the explanatory variable. It's whether or not they thought distance education was, like, good or bad, right? So you have to think to your mind, what is the response variable and what is the explanatory variable, and construct your table in such a way that it makes sense, right? So please keep in mind that when you're doing your projects. So because in our example, we're interested in whether or not prayer itself positively impacted, right, complications. So does it decrease complications? We're then saying that, like, the response variable itself is the complications, but the thing we think explains it is whether or not somebody was prayed for, right? So let's keep this in our minds when we're making our tables, right? So I actually think I ironically may have computed this and I forgot, right? So each column is the response variable. So this is, again, you want to know if the complications occurred, yes or no, right? The cells of the table contain frequencies for the 4 possible combinations of the outcome. So this is the cells. These are cells, like 1 cell here, 2, 3, 4. There are 4 cells that contains all the possible combinations of the outcomes, right? So people who said yes, they had complications, that's an outcome. Well, there are 2 possible outcomes among the people who said yes. It's either they were prayed for or they were not, right? And then your people who said no, that's the outcome, but there are 2 possible groups, those who were prayed for and those who were not, basically, right? So there are obviously only 2 outcomes, but there are 4 groups because there are 2 levels to the response variable, basically. And so this is all the possible frequencies that you can have for all the possible outcomes of the combinations, or all the combinations of the outcome, right? So there are 2 outcomes, but of course there are 4 groups because, you know, the way in which the outcomes happen could change according to each level of the response variable, or sorry, of the explanatory variable, right? So yes, they had complications. Yes, they were prayed for, but they also had complications here and they were not prayed for. So you see these are 2 different, this is the same outcome, but 2 different levels according to the response, to the predictive variable, right? So again, I'll repeat again. This is one outcome, but there are 2 different levels because of the explanatory variable being different across these 2 groups, right? So make sure you've considered all the possible combinations in your own table for your initial reports. And also the reason why you should keep this in mind is because for your chi-squared test, we're going to be using this table to do the chi-squared test and probably next week. And so you should have it in your mind what you're actually testing. So I made this, it looks like I actually computed the thing, ironically, right? So this is me computing it here. This is, so remember, the people who had, who were prayed for is 604, and then those are the complications is 315. So ironically, we're not actually interested in this. We're not interested in this category here. We're kind of interested in this one here because this is where the actual complications occurred. So this is a column this is the outcome we're interested in looking at, right? But then the second group who did not have a prayer but had complications is this category here. So we're really interested in, like I said, this column here, because this is where the actual complications occurred, right? So we can do the same thing with the means. And so, like I said, the standard error for the means looks almost the same because you see that you have the same construction. This is actually, you know, this is the same thing as saying, you know, E1, SE1 squared plus SE2 squared, but this is the SE1 squared here, and this is SE2. So this is this, right? And then this is like this, right? Now it's the same construction, except here you have 2 quantitative variables. So, but you don't know what the problem is. You don't know what sigma 1 and sigma 2 is. So if you wanted to use a z-score, you would need to know what sigma 1 and sigma 2 is, because to construct the z-score, you need to know what the sigma happens to be, and you just don't have it, basically, right? So what you have is the corresponding standard errors, and I should really say standard deviations, not errors. I should be a bit careful. This is standard deviations, not standard errors. It only becomes a standard error when I divide it by root n. This is standard deviation. Because the standard error, as you guys know, like standard error 1 is going to be equal to like S1 divided by root n. So it's not actually a standard error until I divide it by root n, right? So it's actually just a standard deviation. So we have, but the problem is, you know, we don't have sigma 1 and sigma 2, basically. This is a bit of an issue, right? So we cannot use a Z table here, right? We have to use the T table because we're using S1 and S2. I'm going to say that this is not important for you to know per se, but we've assumed that these two things are the same. This is not a trivial assumption. To assume that the sigmas are the same for different groups is not trivial. You don't need to know why I've assumed it in the scope of this course, but it's just enough to know that we've assumed that they're the same at this point. So we're assuming they're the same, which means that when you go to this table here, that's why I'm looking at this thing here. So you don't need to know why we're assuming they're the same, but we are assuming they're the same. And this is why when you look at this table here, it says equal variance is assumed. So I'm looking at this, you're looking at this scenario here. I'm not going to cover unequal variances in this course, so you don't have to look here. I'm assuming equal variances, that, you know, the sigma 1 is the same as sigma 2, which is not trivial, but it's not within the scope of this course. I'm not going to actually talk about it. I'm just going to say that, you know, when you're looking at output, you should only look at the equal variances assumption, because we're not going to cover unequal variances because it's too complex for this course. So this is why I highlighted this. I didn't highlight this part here because we're not looking at it. You can see that when you assume they're equal variances, it does matter because the standard error is a function of what you assumed. And when the standard error, when you assume equal variances, then I can do the following basically. Oops. When I assume equal variances, only then can I really use only then can I use, what do you call it? This thing here, the standard error. So this is what, so we're assuming that I've assumed that this is the true. But I'm not going to explain why, because it's beyond the scope of the course. So just when you see output, make sure you're looking at equal variances. And so you can see that the actual interval is the same basically. Notice that the construction is the same as with the proportions, except I put T instead of Z. You see this is the difference here, right? So you have to be careful and make sure you're using T for the means, but you use that for the proportions, right? So when the when the T-score is chosen, right, when your T-score is chosen, you can actually construct the confidence interval. So you might say, how do you construct it? How do you choose the T-score then, basically? Now I'm going to show you how to use a T-table, basically, for this. And so this is not the same as a Z-table. It's actually a bit different, right? So you can see that if I want to use a T-table, I will go to this. And I have to give you an alpha. So usually, like I said, most of the time I'm interested in the 95% thing, right? So most of the time, you know, I'm going to give you alpha is 0.05. This means that when this is a two-sided thing, basically. This is two-sided. So you're always going to divide it by 2 and look at 0.975 in the table, basically, right? So this is, you know, it's going to be, so that you know, it's technically speaking, it's 0.025, right? It's really 0.025, but the reason why I say 0.9, so it's really this basically. But when you look at the T-table, you're looking at the upper, that gives you the upper tail here, basically. So when you're looking at, if it's 0.25, really what you're saying to this is the 97.5 percentile, right? This is 97.5 percentile for 0.025, right? That's what when you're saying this, you're really saying this is this thing you see here would be, let me write this better. So when you take your alpha to be, like, let's say, when you take your alpha to be 0.05 and you divide it by 2, then what you're actually looking at is like 0.025, but you get the upper tail in your T statistic, in your T table, as you can see from the picture, which means that actually 1 minus this, you're looking at the upper tail, is like 0.975. So look at the 97.5 percentile. That's what you see here, basically. This is this. That's the T statistic you're looking at. You're looking at this thing here, right? So it's looking at the upper tail here. It's looking at this, it's giving you this, basically, right? So this 0.025 is really actually T at 97.5 percentile. It's the upper 2.5%, basically. So this is really saying, look at the upper 2.5%, look at the upper 5%, look at the upper 1% here, the upper 0.05%, the upper like 0.01%, basically, which this is really saying the upper end, basically. So this is the upper 2.5%, the upper 5%, and the upper 10% here, basically, right? So this is why you see the 95% confidence. This is why you see 95% here, right? Because you can see that the lower part here would be like 2.5%, and the middle 90, this is middle 95, basically. This is why you actually see, for instance, that you actually have 2.5 is corresponding to 95% interval. It's because when you put 2.5% up here and you have 2.5% down here, the middle inner part here is 95%. That's why you get 95% confidence level, basically, right? So how do you use this table? You need to be given a sample size, basically. So the degrees of freedom, you know, is going to be related to sample size, right? It's n minus 1. So I need to give you in the question a sample size. that, and then you use that, if I give you a 95% confidence interval, you use the T as 0.025 and you scan to find the appropriate degrees of freedom, right? Which is a function of N basically, it's depending on the sample size. Now, I will say that when you have two samples, that N depends on both the actual samples. You can see that when you have two different samples, degrees of freedom is actually going to be equal to N minus N1 plus N2 minus 1. So actually it's the following. Let me put it on paint. The reason why you have this N1 plus N2 minus 2 is because of the following. Degrees of freedom 1 is equal to N1 minus 1 for group 1, right? Degrees of freedom 2 is equal to N2 minus 1. But then degrees of freedom overall is going to be equal to degrees of freedom 1 plus degrees of freedom 2, which is going to be equal to, for the two, for like a difference of means, basically. What you actually have is N1 minus 1 plus N2 minus 1. But this is going to be equal to N1 plus N2 minus 1 minus 1, which is the N1 plus N2 minus 2 that you see. That's why it looks like that, basically, right? So it's really adding up the degrees of freedom of the two independent groups. So you can do that basically. That's why you got this thing you see here, which means that you need to know the sample size of both groups in order to make sense of your T statistic you put here, basically, right? So I had in the example you have above, going back to the experimental versus control group, notice that their actual degrees of freedom is 38. Over here, you might say, why is it 38? The reason why it's 38 is because your actual sample, the sample, each group is 20, right? So when you take 20 plus 20 and you subtract 2, you get 38. So this is why you can see that for the experimental group, you get degrees of freedom equals, 20 plus 20 minus 2, which is actually 38. So this is how they got that value that you see in the table here, right? It's a reflection that you see here. That I've circled in red, like this thing here. It's a reflection of like what they've done here, which is that both group is 20 people each. And so when they subtract 2, right? So that means that all the values they've actually computed using the software is doing what I've been showing you in class the past a couple of hours, right? So I can formally show you guys, obviously I'm going to, right, how it would work for the T table, the T statistic, right? But first I'm going to say that all of the things I said before with the pi, with the confidence interval for proportions, this is true as well for means, basically, right? So when you have a two-sided test, you're going to reject HO when this difference is not 0. If it's not the case, your interval contains 0. So if your interval does not contain 0, you're going to reject HO. But if it does contain 0, what you're saying is you don't have evidence to actually negate the difference you actually see. You don't have evidence to negate the plausible difference of 0. So you failed to reject the null hypothesis, right? So if it contains 0, it's saying that 0 is possible. So you cannot reject the null hypothesis because you didn't get evidence to do so. But if your interval contains all positive values or contains all negative values, then you have evidence. And I want to point out that in the experiment example, actually we have the interval, and it was something like up here, 6.493 to 23.907, right? So 6.4, let's say 6.49 to 23.91, right? So we actually had in our example for the experiment is the following. We had, example, we had 6.49, I think, to 23.91. Notice that these are all, this whole interval is bigger than 0, right? So this interval really doesn't cover 0. So what you're actually, you're gonna reject HO basically. What you're gonna say here then is that actually you have evidence to show that the group 1 performed better than group 2 because all their values are actually positive. So it looks like the people who were told to have gains perform better in their IQ test than those who were told they don't have gains. And because 0 is not in the interval, and in fact, they're all positive too, right? That's how you know the direction of the effect, because they're all positive values, right? So if they're all negative values, you'll be saying then that the control group did better than the experimental group, but it would still be a reject HO. It's just, that's not what the data actually showed in the actual mean test, right? So I just want to point out that, again, a confidence interval is implicitly a two-sided interval, but you can address, again, one-sided tests using a two-sided interval. So let's write this down again. You can address, you can address one-sided test in the way that I actually just told you. Well, look to see, right, the sign of the actual test and of the interval. And if it's all positive values, well, you know that if you're doing a one-sided test in some sense, you can then say, well, look at the test is actually showing us that, right, all our values are actually bigger than 0. So we reject the null hypothesis and conclude the alternative that is bigger than 0, basically. But if all the intervals, all the values were negative, you can say, well, look at what we see. The values are all negative. It doesn't cover 0. We have evidence to show that, like, oh, it looks like mu1 is less than mu2. So we would accept the alternative, basically. So you can, of course, perform the same test, but really you're doing it using a two-sided interval, basically, right? And so you could do this, again, using the confidence interval to answer these questions here, or you could use the test statistic, which is what you saw before. It's, again, defined like before, except this is putting the test forward. You have, mu1 minus mu2 is equal to 0 versus the alternative. Mu1 minus mu2 is not 0. So this means that this thing here is equal to 0, basically. That's why you actually have your actual test statistic is something like the following. T is equal to the estimate divided by the standard error, basically, which is given to you as what you see here, right? So it looks a lot like what you saw before, right? Except now you're not looking to, you don't have degrees of freedom n-1, you have degrees of freedom n1 plus n2 minus 2, because you have 2 different groups. But like I said, it's the same idea with the z-score. Whether or not you multiply by 2 depends on the actual direction of the effect. And due to the interest of time, I'm going to hold off on showing you guys how to find the p-value using the t-table, because that's not obvious. It's not as obvious as the z-table, because you can see that this is not a table of p-values, whereas this is a table of p-values, right? So I'm gonna hold off on showing you guys how to actually compute this, how to compute the p-values using this table until next time, just so I don't cram things in the last minute. It doesn't make any sense. So this means the quiz for next week will just be up to slide 33. We're not going to see the last 2 slides because I didn't have time to cover it today. So this stuff we'll talk about later on, right? But I'm not going to, and I won't do the p-value stuff just yet because that's a bit early. Oh yeah, sorry. Next week is Good Friday. So the week after that, sorry about that, guys, which means I cannot put the quiz next week. So I'll put the quiz on the makeup week, right? So the makeup lecture. And whenever that is, that will be the next week quizzes. Because I realized actually, yeah, it's a Good Friday, Michael. It's Good Friday next week. Yeah, so that means we don't have class, and I'm not going to ask you guys to do the quiz, obviously, because I cannot put a quiz on Good Friday. So I'm going to make an announcement, and then whatever the makeup lecture is, that's when the actual quiz will be. But have a good afternoon, everyone. Bye. And if you have any questions about the final reports, please send me an email or the initial report, sorry, or put it in the actual discussion board. Have a great weekend, guys.